Here we will see again some basic mathematics and basic concepts related to Fourier series and Fourier transform. However, I discussed this already in a lecture, I think it's somewhere in January and February, but I think to go further this basic is needed to revised again, so that's why it's a sort of revision lecture. So I will start with some basic periodic functions. So the basic periodic function we know are the sine and cosine waves. So on the left panel, as you can see, this is a sine wave function. As a function of time it is plotted, and you see that it has a period 1 second, and if you see that it completes one cycle in 1 second, so its a period is 1 second. So that means it repeats the pattern after 1 second. Similarly, on the right hand side, if you see that function, it repeats the same pattern. Here is one cycle completed in 2 seconds, then it repeats the same pattern, and then it goes on. So it has a period of 2 seconds, that means the frequency is 0.5 Hertz. So we can write mathematically speaking any function as a periodic function if this function repeats itself after a certain interval of time or after a certain interval of space. So for example, as it is written here, that f(x) plus kp is equal to fx, where k is an integral integer value. K can be 0, plus minus 1, plus minus 2, and p is the fundamental period. Fundamental period means the smallest period or smallest time or smallest space after which the pattern is repeated. So in case of our previous example, the fundamental period was 1 second in one example and 0.5 2 second in one example. So mathematically, Fourier series or Fourier theorem says that any well-behaved function, well-behaved means it is continuous and it is defined at each point in time or in space, can be represented or expressed in the form of sum of sine and cosine functions, as written here. Ft is your periodic function. This is the summation between from n equal to 0 to infinity an cos nt plus bn sin nt. So these are your sine and cosine terms. An and bn you have to determine. These are the amplitude related with these sine and cosine terms. So why sine and cosine? Because sine and cosines have an interesting property. That property is that they are most simple waveforms in mathematics. Their values are bounded between -1 to +1, and the interesting thing is that a sine wave remains a sine wave of the same frequency when you multiply it by a constant. If you multiply a sine omega t by 1t or 2t, the frequency will not change. Or if you add it to another sine wave of the same frequency, then it will still remain the sine wave of the same frequency. Or differentiate or integrate it or shift it in time, the frequency will not change. Actually, the Fourier series was discovered or was first used by Joseph Fourier in the study of heat wave propagation or propagation of heat in the earth. So just now we will see that what I was saying to you, just through some you can say some tutorials or some sort of examples here are plotted of sine waves. This has a frequency 0.2, and I plot another sine wave with certain frequency but different amplitude, and then when I sum them up, you can see that I have same sine wave with the same frequency but with the same amplitude, because amplitude has changed because but I kept the amplitude in a way that the amplitude remains between -1 to +1 in of both the sine waves. Now in this case, if I change their frequencies, I am changing their amplitudes, as well as now if I change the frequencies of the two sine waves. So one is y1t, the blue one, and the orange one. So blue one is the low frequency one and the orange one is the high frequency one. So if I sum them up, these two sine waves of different frequencies, that is how our summed function looks like. And now the same thing if I do and keep it repeating for n number of times, different frequencies sine waves of different frequencies are added all together, so what you get is something like this. So that is what looks like very close to a square wave. So that also gives you an idea that why Fourier, or why we saw that a sine wave can be represented, or sorry, a periodic function can be represented as the sum of sines and cosine. Here we are just writing it as the sums of sine waves. This is a periodic function, this is a square wave, this is a periodic function, it repeats the same pattern. So this proves experimentally, or by demonstration, that we can represent a periodic function as the sum of sines and cosines. One more example with different frequency components, adding again together, you can find it that it represents a sawtooth wave. Again, it is a periodic function. So we have seen by this example that any periodic function, at least two periodic functions, square wave and this sawtooth wave, can be represented as sum of sine terms. So mathematically, we can write this ft as summation over n equal to 0 to infinity an cos nt plus bn sin nt, because we chose sine and cosine terms, as I said before, they are basic building functions in mathematics. So in terms of mathematics, I will not be deriving this, but you can appreciate it, and you have already studied this, and we already discussed this detail in the last class. So it is just for your revision. As you can see that this is the Fourier series. We can estimate an and bn if we multiply it both side by cos mt. In this case, it will become like this, and we can use these orthogonal properties of sine and cosine function between minus pi to pi. So this will give us an is equal to 1 by pi minus pi xt cos nt dt. So this we have discussed in the last lecture when I took. So this is just for revision, as I said again. Similarly, we can determine bn, and I also discussed that why the 0th term will be half by a0, and I think I have shared this PDF with you. So any function, periodic function, can be written. So keep in mind, not any function, periodic function can be written as the sum of sines and cosine waves. The only condition is that xt should be integrable between the range minus pi to pi, because if xt is not integrable, these values of an and bn we will not be able to estimate. So the only condition for a periodic function to be represented as the sum of sine and cosine is that it should be absolutely integrable. That means the value should be finite between this, the integration, the value of the integration between minus pi to pi should be finite. It should not be infinite. This we did with a period of 2 pi. When the periodic function has a period of 2 pi, this can be extended for a periodic function with a general periodicity, for example 2t. In this case, we will need to make some variable changes here. Yt, it should be ys, so xt we can write in place of directly t, we can replace t as s, and where s is equal to t by t divided by capital 2 pi. So we are making change of variable here again, as I said in the last class. So ys can be written as 1 by 2 a0 an cos ns. So essentially we are replacing t by s, where s is equal to t by pi, t multiplied by divided by t. And then similarly again an and bn can be estimated by multiplying sines and cosine both sides one after the another, then we can estimate an and bn. The interesting thing is now coming is the energy. So the total energy in the signal between minus pi to pi can be written as minus pi integration between minus pi to pi x square dt. So this is essentially coming from the amplitude term, that we can write energy as the square of the amplitude and sum over the total interval, total time interval. But we know xt can be written as half of 0 plus, this is the Fourier series expansion of xt. So you can replace xt from this equation to here and then do the integration. But we know from the property of cos square nt and sine square x, their integral between minus pi to pi is equal to 1. So essentially these terms, these integration terms between minus pi to pi cos square nt dt and b square and minus pi to pi sine square nt dt, they will become 1. So what we will have essentially is pi, the integration is equal to pi 1 by 2 a square a naught square plus the summation term a square n plus bn square. So this is Parseval's relation that tells us the equivalence between the energy in time domain and the frequency domain. To generalize this, we can write it in terms of Cn, where Cn is equal to half of a square n plus b square n square root of the entire thing, and C0 is equal to A0 by 2, and the total energy of the signal can be written as 2 pi, because this 2 pi is needed outside to make the because otherwise it will become 1 by 4 when you will square it. So that's why this 2 pi is needed outside. You can see this mathematical manipulation, but this is a very important relation. This is telling us the total energy can be written as in different frequency component, where n belongs to the frequency components. So this is the total energy. This results tells us the amount of energy dissipated over a standard time period between 2 pi, but the energy between minus infinity to infinity will be again infinite, but it is enough to have the energy between minus pi to pi. So that will be finite. That's, as we can see, this is finite. Or we can focus on another term which we call power, because power is easier to explain, because power is with respect to time, energy loss with respect to time. So that is, or with respect to time interval in this case. So total energy between minus pi to pi divided by the total time interval, which is 2 pi. So 2 pi will be cancelled, that is just summation over n c square n. So this is total power contained in the signal xt, where n represents the frequency term. So this is important. This is total power, n represents the frequency term. We can write frequency n by 2 pi. N can be written as 2 pi f. So this is sort of angular frequency actually. So if you write n equal to 2 pi f, so 2 pi will be cancelled. It will become a linear frequency term. So if this, as you see, the summation term is giving you the total power, but what c square n I'm sorry, is giving to you, it is giving you the contribution in the total power from the Fourier series of xt with frequency n, or n by 2 pi. So the contribution of a particular frequency in the total power. And if we plot this, these are some discrete frequency components. As you can see, as n will change, this frequency will change. So these are discrete. Keep in mind, this discrete and continuous will come later. So this is telling you the power in the signal at this frequency 1 by 2 pi. The next one is telling you the power in the signal at 2 by 2 pi. The next one is telling you at 3 by 2 pi. So like this, and when you square and then sum up them up, this will give you the total power in the signal. And this we can apply to the functions of general periodicity, because the previous case was the function of 2 pi periodicity. In this case it is a function of general periodicity, where we can write the Fourier series in like this, and the total power in this case will be between minus t to t, which will be again in the time domain it will be the integration between minus pi to pi x square t dt, but in the frequency domain it will be, when we have seen from the Parseval's relation, that it will be in the frequency domain 2t infinity sum over n equal to 0 to infinity cn square. So the total power in this range, if we divide it by 2t, so the total power will be integration 0 to infinity. If you cannot see on this side, this will be cn square. So cn square is the contribution to the total power from the nth frequency component, as I said. But in practice we do not always have periodic function. So far we were discussing periodic function, either it has a period of 2 pi or it has a period of 2t. So if it is a non-periodic function, I'm sorry, if it is a non-periodic function, we cannot express it in the terms of Fourier series directly. We have to make some transformation. That transformation is that if we define a new function which is identical to xt over a certain interval of time, and then we make it periodic after that time. So this is the function is written here like x star t, x star capital T, function of t, small t, xt, x function of small t, minus t between, so it is identical to your original function between minus t to t, between the time interval minus t to t, and then it is a periodic function. That is how we write a periodic function. As you can see, x is x star capital T function of t plus 2p capital T is equal to x star t. So it will repeat after every 2t period. So the period is 2t, so every 2t it will repeat itself, 2 capital T. Since x star t small t is a periodic function, then we can express it in the form of Fourier series. So again you can see here, so x star capital T function of t is a periodic function. We can write it in the form of Fourier series here with the summation of n equal to 0 to infinity a n cos 2 pi fn t plus b n sin 2 pi fn small t. And for fn we can write n by 2t. So in place of n we are writing fn, where, as I said before, f can n can be replaced in the form of linear frequencies. So in this case it is n by 2t, earlier it was n by 2 pi. And we remember the Euler's formula, where we can write cos functions and sine function in the form of exponential functions. So this is the, on the left hand side top you see x star t as the Fourier series, and if we use those Euler function in place of cos 2 pi and sin 2 pi fn t, we can write it exponential of 2 pi fn t multiplied by a n, where a n is generically written like this. And we know that the values of a n from b n from our previous case, where we have seen for the coefficients a n and b n for the generic case of Fourier series, they are, if x star t is a periodic function, we can write a n and b n like this. So these values are again, along with the Euler's formulation, are kept inside, are put inside this relation a n is equal to 1 by half a n minus I b n for n equal to greater than equal to 1. So if we insert them there, so what a n becomes essentially is 1 by 2t integration between minus capital T to capital T x star t function of small t e to the power minus 2 pi fn t dt. So you see that between minus t to t x star capital T function is periodic and it is equivalent to xt. So we can write this integration in the form of xt itself. So 1 by 2t from minus infinity to plus infinity, minus capital T to capital T x function of t e to the power minus 2 pi fn t dt. So then again we have, so in place of a n we have these values, as I said before, and we can replace these values of a n in this term in what is written here on the left hand side, and then xt is equal to xt star t will become summation over n equal to minus infinity to infinity. Here we are inserting value of a n which is in the form of integral between minus t to capital T xt e to the power minus 2 pi fn t dt. Another exponential is coming from here, e to the power 2 pi fn t, which is from the original definition here, and 1 by 2t is the multiplication term which was outside. So in place of 1 by 2t we can write it as delta fn, which is frequency resolution. So delta fn is 1 by 2t, and essentially when our t becomes infinity, the summation becomes integration. So this summation term on the left hand side is becoming integration, and we can write xt is equal to minus infinity to plus infinity pf in place of pf. This inside integration term is essentially pf, and the outside e to the power 2 pi fn t, delta fn will become df. So essentially it looks like this, that xf can be written as integration minus infinity to infinity pf e to the power 2 pi ft, where pf is integration between minus infinity to infinity xt e to the power minus 2 pi ft dt. So essentially they are forming the transform pair. So here we see that a non-periodic function can be written as in the form of Fourier integrals, which essentially form a Fourier transform pair. So this one xt pf is equal to minus infinity to plus infinity is the forward Fourier transform pair, forward Fourier transform, whereas the xt is equal to minus infinity to infinity is the inverse Fourier transform. And you must have seen a very generic form of these Fourier transform written like this: xt is equal to 1 by square root of 2 pi minus infinity to infinity g omega e to the power minus, sorry, e to the power I omega t d omega t, which is the inverse Fourier transform. So this is coming from essentially from the change of variable. We are changing f to omega, so this 1 by square root of 2 pi is essentially coming from there. So essentially it will come 1 by 2 pi, but to equally distribute it on the forward or on the backward, you write it 1 by square root 2 pi in the forward and 1 by square root 2 pi in the inverse Fourier transform. So these are the Fourier transform pair which we do with the non-periodic signal. So this we will see in the next, that the condition for, in the next class, that the condition for Fourier series to exist is that the function should be integrable, it should have a finite value in the time period, in the interval, and it should be a periodic function. For Fourier transform, it doesn't have to be a periodic function, but it should be integrable. It should be integrable, otherwise if in your function is not integrable, we cannot have a Fourier transform pair as well. So in the next class we will discuss about energy and power in case of Fourier transform pair.